Hello. In this video I'll be solving problem set 3, problem 1, and started this video before and then I realized the mic was turned off, so some of this is already done, but I'll start from the beginning again with the rest of this. So here, in this circuit, we are trying to design a circuit that implements F using a two-level AND/OR circuit. So for the most part, this circuit's almost already there. We have an AND with an OR circuit and something a little funky here, and we just need to figure out how to get this to two levels. Well, G1 and G2 can combine into one AND gate, so this would just be a 3-input AND with A, C, D. And then we potentially have G3, and as this work already shows a little bit, and this is very close to being an AND gate already, an OR with its output complemented and its inputs complemented is an AND gate. So if these are complemented and this is complemented, we can just change G3 into an AND gate and just make sure we keep this outside inverter to make B bar. So our circuit for problem 1A so part A is going to be, we're going to put A, C, and D together from here, and then we're going to want C, D, and B bar going into a separate AND gate, so C, D, B bar, which we're going to want to show every transistor that we use, so I won't be using the B bar there. So A, C, D, and then we're going to have C, D, B is going to be inverted, and we're going to make that. So, and then we're just going to want to put these both into an OR gate. So we got that. Put that down. And we solve for F. So here we got F is essentially equal to A, C, D, or B bar, C, D, which gives us a how to think about this, sorry. This is our SOP expression. So, now what do we need to do next? That's done. We need to design a circuit that implements F using a two-level NOR circuit. So, we have one of two approaches we could try. One approach, which I'm never a terribly big fan of, is trying to convert this directly into a two-level NOR circuit by changing gates around. I'm basically going to be plugging in lots of transistors, or NOT gates, and pulling them out, and that just doesn't seem like a lot of fun. So rather than do that, let's turn and focus at this. Well, what do we have here? We have an SOP expression that we know corresponds to a two-level AND/OR circuit, or we wanted to, we could simply change this to a two-level NAND circuit just by replacing this with an AND, this with an AND, and that with an AND. So let's do something similar by first solving for the POS expression and then solving for the two-level NOR circuit. So what you should notice, hopefully, we have C, D, C, and D. We put these two together, we can just distribute this A or B bar out. So this is going to be A or B bar and C, D. Well, we're actually already done. We are at our POS expression, so this was done with one distribution, and this is our POS solution. Because we can think of the single C as a sum term, and we think of our product of sum. Yeah, so this is a single sum term and this is a single sum term. And now we know how to implement this with an OR circuit. So I'm going to do that first. So we're going to do a single level, two level OR AND circuit. So this is equal to A, B, and C, D. And we will want to put a, well, this is not our final circuit, so I'm just going to put the complement there. And we will put that, and we'll have our OR circuit for that. And then all of these three are just going to go into an AND. So C, D, and you, my friend, will come down here. All these are going to feed into an AND gate. So that's our two-level OR. So this is our OR AND circuit, which we can easily convert to a two-level NOR by complementing here, 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 and here. So this will change to a NOR. But if we do that, we will need to add inverters here as well. So this becomes our NOR, and we will convert this to A, B, and this time I will actually draw all my transistors. So we're going to have A, B going into this NOR gate, C going into an inverter. Oh, shoot, sorry, need an inverter here for my B, D going into inverter, and then all of these are going to feed into our new NOR gate up there. So bring this down. And that solves for F. So this is our two-level NOR circuit. And so finally, for part C, we need to calculate the ratio of transistors used in design A to design B. Well, each of these AND gates is composed of a NAND gate with a transistor afterwards. So what we learned is a NAND gate requires one transistor per input, so that's going to be 3, plus one additional transistor, so that's going to make 4, and then we're going to need a NOT after this NAND to make that 5. So this is 5 transistors, 5 transistors, 1 transistor for the NOT, and this is going to be a NOR with a NOT afterwards, so this is 2 transistors. Up here, down here, we've got 1 transistor for a NOR, 1 transistor for a NOR, 1, 1, 1. So 1 transistor, 1 transistor, 1 transistor, 1 transistor. And this comes out to be C, so design A to design B is going to be 5 plus 3 is 13. 2, 1, 2, 3, 4, 5. And that finishes what we need to do for problem 1.